Hello, and welcome back to A Slice of Physics. Having discussed the basics of magnetism, we're now ready to discuss the magnetic field from a current, specifically in a long, straight wire. First, we will introduce some notational aspects. We are talking about three-dimensional directions on a two-dimensional paper or two-dimensional screen. So we have some notations that we use for that. So we'll introduce you to that. And then we will talk about the magnetic field from a current in a straight wire. First, we will tackle its direction, which gets us to the first right-hand rule. And then we'll talk about the magnitude, which is simply an equation. And then lastly, we will wrap up with talking about how we go from magnetic field lines in a region of space to a magnetic field vector at a point, just like we did for electric fields a few weeks earlier. All right, so let's take some examples. Let's say that there's a wire, and I'm going to take the wire like that. And let's say the current goes to the left. No problem, I can denote it like this, and I'm done. If I have a wire like this, and the current goes to the top right, I can show it as an arrow, show I, and I'm done. But what happens if the wire is actually going into the page or the slide and coming out of the slide? So all we see is the cross section of the wire. And let's say the current is coming out of this. Or I have the same kind of wire here. Cross section is all I see. The wire itself is perpendicular to the plane of the slide going in and out of it. So I see its cross section. And the current is going in. How do we represent this? Well, when it's coming out, we show the circle representing the wire, and then we show a little dot at the center. And when the current is going in, we show the circle representing the wire, and we show an X. So let's summarize. A dot means coming out, and an X means going in. And this, you can make sense of this by thinking about an arrow. So if an arrow is flying straight toward you, you're going to see the tip of the arrow, which is represented by this dot here. And if the arrow is flying away from you, you're going to see the back of the arrow, which means you're going to see the feathers that are stabilizing its flight. And usually those feathers are put in an X pattern, so that's what you will see. Okay? So X means going in, dot means coming out. And there is a circle around it when it denotes a current. We are also going to be talking about other things right away. So we're talking about magnetic field from a current. Magnetic field is denoted by the symbol B, and a couple of things about it. It's a vector, so it's got magnitude and direction. So I have to be able to specify the direction of magnetic field. And it's got magnitude, and the SI units, by the way, for magnetic field is Tesla. We'll talk more about what that is. It's written as capital T. And it's named after Nikola Tesla, the physicist who did a lot of experiments with magnetic field. By the way, Elon Musk's car company, Tesla, is also named after the same scientist. So now if I have a region of space where I have the magnetic field pointing in this direction, no problems. I can just do it with an arrow. If it's pointing like this, it doesn't have to be a straight line. It could be a curve, as we saw around a magnet. I can draw it like that. So these things I can represent on a piece of paper with no issues. But what if the magnetic field in this box is coming out of the page? How would I show it? Well, we have our symbols now. So for coming out, I show a series of dots. And in this region of space, if it's going in to the page, I will show it as a series of X's. Okay, so X's always mean going in, dots mean coming out, currents have a circle surrounding it. So a dot with a circle around it means current coming out, and X with a circle around it means current going in. Simple dots or simple X's mean a vector going out or in. And in this case, the vector is magnetic field. We're also getting ready to talk about forces of magnetic fields, Those are called magnetic forces. And as you know from physics 1, force is a vector. So sometimes we'll use these dots and X's to show the direction of a force vector. So from the context, you will know if these symbols without circles around them are representing either magnetic field or force. By the way, just a quick aside here, currents have magnitude. You guys know that it's measured in amperes, and they have direction. We're talking about the direction of current all over here. We've talked about the direction of current in a circuit. And yet they are not vectors. That might seem confusing at first, but think about it this way. If I have a 3 amp current going to the right, meeting a wire that's going straight up, and a 2 amp current coming in another wire to the left like this, you guys know from the junction law that the total amount of current coming in has to equal the total amount of current going out. So the current in this top wire has to be 5 amps. Well, if these were vectors, the 3 and 2 have opposite directions, so they would not be adding like scalars. So this tells us that current is not a vector, but it's a scalar, even though it's got magnitude and direction. And one more quick example, if I just take these wires and move them so they're pointing like this at some angles, the current in this top wire is still going to be 5 amperes. So the direction of the current is not relevant to how we add up currents and so on. So it's not a vector, even though it's got magnitude and direction. All right, so now we've got the notations. Let's talk about how we discuss the the direction of magnetic field from a long current carrying wire. So if I have a wire here and the current's pointing to the right, we will use the first right-hand rules. So we want to get the direction of B from this I. Okay, so you know that every current has a magnetic field. We talked about that as a fundamental property of current. If you have a current carrying wire and you bring a compass close to it, the compass deflects. So every current has a magnetic field. Let me write that down. Every I has a B. And we are talking about how we determine the magnitude and direction of that B magnetic field. So first, let's talk about the direction. So to do this direction, we use the first right-hand rule. There is a second right-hand rule we're going to meet shortly, but let's now focus on the first right-hand rule. So for the first right-hand rule, the steps are like this. First, you hold your right hand, by the way, and apologies to those of you who are left-handed. The first right-hand rule only works when you use your right hand in a thumbs up position, let's say, as a thumbs up. You guys all know what that means. Please follow along. It's hard for me to draw what I'm talking about here. So just hold your right hand and hold it in the thumbs up position, which means your thumb is point straight and the remaining fingers are curled. 2, grab the wire and point your thumb in the direction of I. Again, you have to give me some liberties with my bad drawing, but if I bring my hand right next to the wire, then you can grab the wire or you can put it right next to it rather than crowd the diagram. I'm going to put my thumb over here, and the thumb has to point in the direction of the current, so it'll be pointing to the right, and my fingers will be curled like so. The rest of my palm is here. These are my fingers. I guess there should be one more finger. All right. Not a great drawing, but hopefully you get the idea of what I'm talking about. So this is the thumb, and it's pointing in the direction of current, and my fingers are curled like this in this direction. So that gives me the direction of magnetic field. The fingers give me the direction of magnetic field. Thumb is pointing in the direction of I, and fingers give me the direction of magnetic field. So step 3 here, curled fingers point in the direction of B. So in this case, my magnetic field direction is going to be going this way. So if I take certain points, let me take a few points here and talk about what the direction of the magnetic field will be. So if I have a point over here, actually, let me not draw an X. So I'm going to show 4 points here with red dots. 1 point over there, 1 point here in front of the wire between you and the slide, 1 point here in the plane of the slide below the wire. Okay. So as your fingers are curling, if you loosen them a little bit, you will see that the direction of B above the wire is going to be coming out. See that at the very top, your fingers will be pointing out. Here, at a point in space between you and the slide, the direction of magnetic field will be pointing straight down because your fingers are pointing down. At the bottom, as you curl your fingers back into the page, here it'll be pointing into the page, and then behind the wire, behind the slide, it'll be pointing up. So hopefully that makes sense. You will see some more examples here that'll bring this home. So let me use our new symbols that we have learned to identify those things. So the direction of magnetic field here will be out, which means it'll be dots. The direction of magnetic field below the wire in the plane of the page will be X's because it's going into the page. And then the direction of magnetic field in between the wire and you above the slide is going to be pointing down. All right. So that's the direction. Let's take another perspective of this. So let me take the direction of the wire like this, and the current is going into the page. So this is I is into the page. That's what that symbol is telling you. So now I will hold my right hand with my thumb pointing into the page. So do a high five, rotate your hand so your thumb is pointing into the page, place it right at the wire. And if you do that, you will have your thumb pointing into the page like so, and then your fingers will all be curling like this around your palm. So this tells you that the magnetic field direction is going to be like that. So when you have a wire that is got a current going in, the magnetic field direction is going to be in this direction, so it'll be clockwise. And if I have the current coming out of this slide, so if the current is coming this way, now I hold my thumb coming out of this page and my fingers will be curling this way. So if I have a wire like this, the magnetic field for it will be counterclockwise. By the way, this counterclockwise is the magnetic field line, right? So if I go further out, it's still going to be counterclockwise. If I still go further out for this one, it's going to be clockwise. So those are magnetic field lines, which tells you what the magnetic field looked like in a region of space. Now, if you want to get the magnetic field at a specific point, the rules are the same as before. So if I want the magnetic field at this point, then it's a vector. It's not going to be a curve. It's going to be a straight line that's going to be tangent to that curve and pointing in the right direction based on how the fingers are curling. So it'll be that over there. Over here, it'll point straight up. Over here, it'll point straight down. Over here, it'll point straight to the left. So similar to how we did the electric field, it's just a tangent. So you can go from magnetic field lines to magnetic field vectors. And for this guy, with the current coming out, the magnetic field vectors at various points will look like that. Okay, so that's how you go from whether it's clockwise or counterclockwise to what it is at specific points, which will point up or down or left or right or at some angle. All right, the last part is figuring out the magnitude. So the magnitude is simply given by an equation where it says B equals mu naught I over 2 pi r. And the important thing is to understand the context of these equations. So let me give you that. This B here is the magnetic field at a point at distance R from a wire carrying current I. So if the current in this wire here is I, and I want the magnetic field here, this is R. And if I want the magnetic field here, this would be R. So let's call this R1, R2. The magnetic field here would be B2 and B1 here. All right, so that equation gives you the magnitude of the magnetic field, and it depends only on two things. I, the current in the wire, R, the distance of the point at which you want the magnetic field from the wire. And then this mu naught is just a universal constant, just like you had epsilon naught when you were working with electric fields. You've got mu naught when you're working with magnetic fields. It's called the permeability constant, and it's got a value of 1.26 times 10 to the negative 6 Tesla meter over amp. And you can see that if you multiply this mu naught times current in amps, the amps will cancel, and then you divide by 2 pi r, where r is in meters, so the meters will cancel, and you'll get the magnetic field in Tesla. We'll take an example of this in the next video to bring this all home for you. All right, so in this video, we talked about the magnetic field line from a current. We introduced the notations for representing 3D things on a 2D paper. We looked at the equation that gives us the magnitude. We looked at the first right-hand rule, which gives us the direction of the magnetic field. And we talked about how we can go from magnetic field lines in a general region of space to a vector at a specific point. Thank you.